we've been talking about systems of diffuse, right? So we've been talking about system of diffuse, and in particular, we have seen that if you have a system of linear ODEs, right? So systems of first order diffuse, right? So system of first order diffuse, it can be written as the following equation, like d by dt of x1, x2 up to xn is equal to a matrix p11 of t up to p1n of t dot dot dot. Okay, so pn1 of t up to pnn of t multiplied by x1, x2, xn, right? So plus the right hand side g1 of t, gn of t. So it's kind of natural to consider such equation. Now what happened here is that you would like to write this one as an x, so that's dx over dt, a vector, is equal to a matrix p of t. This is the whole thing is the matrix multiplied by x again, right? So multiplied by x again. Okay, so multiplied by x again, so x of t plus the g of t is a vector. So that's kind of a vector matrix equation. This equation written in this way is in a vector matrix form, right? So that's the vector matrix equation. Okay, so we can reduce our problem to solving such vector matrix equations. Okay, so we can reduce our problem to solving such vector matrix equation. So that means you would like to understand better about vectors and matrices, right? So understand better about vectors and matrices. And this is a part of mathematics in algebra, which we're going to call it is the linear algebra. Okay, so that's the topic we would like to cover for today's lecture. Okay, so what's linear algebra? Okay, so what's linear algebra? Well, the linear algebra consists of, first of all, the matrices, right? So here, I like to emphasize that within your class, most of the linear algebra information I was going to test you is about either 2 by 2 matrices or two-dimensional vectors. Okay, so two-dimensional vectors, or it's about 3 by 3 matrices. Okay, so that's or three-dimensional vectors. These are the worst scenarios, worst case scenarios that you will be asked to consider within these lectures. That we won't, of course, you can consider n by n matrices, right? So, right, n by n matrices or n-dimensional vectors, right? So, but this is kind of not considered within this class. The only thing you need to consider in this class are either 2 by 2 matrices or two-dimensional vectors, or 3 by 3 matrices or three-dimensional vectors. How are we going to consider them? Well, if you have a matrix, let's say a matrix A in 2 by 2, that probably looks like this: A12, A11, A12, A21, A22. So a matrix is nothing but you put all these numbers in rows and columns. You form capital letter A just to denote a collection of all these matrices, all these matrix elements, rows and columns, right? So, and it can be 3 by 3. If it is 3 by 3, it will look like A11, A12, A13, right? So A21, A22, A23, right? So A31, A32, A33, right? So that's kind of 3 by 3 matrices. And matrices are vectors are a special form of matrices. For example, if you have a vector like this, then this is like a 3 rows, 1 column. So 3 by 1 matrix. So we use this as a number of rows, this as a number of columns. Okay, so that's kind of, so for example, this is 3 by 3 matrix. This is 2 by 2 matrix, right? So you can have, for example, A11, A12, A21, A22, A31, A32. This is like a 3 by 2 matrix. Is that going to travel? Okay, so these kind of collections of rows and columns into numbers are called matrices. Okay, so are called matrices. So the most important thing is how you are going to operate on matrices, right? So how are you going to operate on matrices, right? So here's a, there are several operations of matrix. So given A is a matrix, right? Suppose you're given a matrix A, right? So A is a matrix. Then there are several different ways to operate on this matrix. One way is we call it the transpose. Okay, so the transpose of a matrix A transpose is a good property. Okay, so this is a very simple, simple principle. But what's the A transpose? Suppose A is like A11, A12, A21, and A22. Then the transpose simply means that you're going to keep the diagonal. You're going to switch the off diagonal. So that A transpose becomes A11, A12, A12, A21. So the transpose simply means that in the transpose, a column in the transpose is originally a row. A second column here is a row. So you change rows to columns, you change columns to rows, right? So if you have a vector, let's say x is equal to x1, x2, x3, how are you going to have the transpose? Well, again, the same thing. So rows are going to be columns, columns are going to be rows. So x1, x2, and x3. Is a good fabric? That's the transpose, right? So what happens in general? So if you have a B matrix, which is P1, P11, P12, P21, P22, and P31, P32, you're going to have B transpose. Then it's going to be P11, P12, P21, P22, right? So P31, P32. So you change rows to columns, you change columns to rows. Is a good fabric? Okay, so that's what we call it the transpose. Very simple way to operate on matrices. Another type of operations is called conjugacies. By conjugacy, it means that you just conjugate every element in A. For example, A is A11, let's say A12, A21, A22. And what's the conjugacy? You take a bar here. So it's like the complex number conjugacy, A12 bar, A21 bar, and A22 bar. So that's what we call it the conjugacies. Okay, so the other joint operation is like a conjugacy matrix together with transpose. So the conjugacy first and transpose. So here's a nice example shown on the lecture notes that if the number, the matrix A has 4 numbers there, 3, 2 minus I, 4 plus 3I minus 5 plus 2I, what's the transpose? Well, the transpose means you keep the diagonal, you switch the off diagonal, right? So you switch the off diagonal. And if you want to calculate conjugacy, you just do conjugacies for each of the complex numbers here. And what about the, so this is the conjugacy. But adjoint, it means that you just take both the transpose and the conjugacy. So that's the adjoint. Okay, so these are 3 different types of operations. Transpose, conjugacy, and adjoint is 3 very important types of operations. Okay, so now we would like to build an algebra, right? So our goal is to build an algebra for matrices, right? So what does it mean, an algebra for matrices? An algebra simply means that you have to say, well, what is A equal to B, right? So how do you say equality A is equal to B? If A is equal to 1, 2, 3, 4, and B is equal to 1, are you going to say A equal to B? Not, right? So that simply means because the A and the B doesn't have the same size for the matrices. Now, if A is 1, 2, 3, 4, and B is equal to 2, 1, 4, 3, are they going to be the same? Well, they have the same size, but their numbers are not going to be equal to each other. So again, A is not equal to B. So what does it mean A is equal to B? Well, A is 1, 2, 3, 4, and B has the same size as 1, 2, 3, 4, together with their corresponding numbers. So in that case, we say A is equal to B. Is that good for everybody? Okay, so this is how we say equalities of 2 matrices. Means that every element in the matrix has to be equal, right? So what is a 0 matrix? Well, a 0 matrix is simply means, okay, so let me write it in this way. A 0 matrix is simply means everything is 0 inside the matrix. Is that good for everybody? What's the identity matrix? Let's say I, number 1. Well, identity matrix means that you have ones on the diagonal and offs on the, and the zeros everywhere else. This kind of matrix are called identity matrices. Okay, so this kind of identity matrices. And we also have this notion of a scalar multiplication. So now you have the matrices. I mean, you have the identity of equality of two matrices. You can do the zero matrix, identity matrix. So that's you have to talk about, for example, what is the addition of two matrices? Well, if you have A plus B, right? So it naturally, for example, 1, 2, 3, 4. Yeah, can you add this matrix 1, 2? Well, this is not possible because these two matrices simply doesn't have the same size, right? So if they have the same size, it means they should have the same number of rows as well as the same number of columns. Only in that case, we say these two matrices have the same size. Is that good, Trevor? If they have the same size, you can simply do an addition. So A plus B is 1, 2, 3, 4, plus let's say 3, 2, 4, 3, 1. Do you add these two matrices? That's 3, 6, 6, 5. So you just add the corresponding terms inside the matrix. 1 added to 2, 3 by 3, 4 by 1. So that's the summation. Is that good, Trevor? Right? So that's how you add two matrices. Now, if you have addition, you have multiplication, subtraction. So, for example, the same thing, 1, 2, 3, 4 is going to minus 2, 4, 3, 1. You just subtract the term by term, minus 1, minus 2, 0, and 3. So that's kind of, you just subtract the term by term inside the matrix, right? So that's subtraction. Now, what about multiplication? If you have a matrix A, you have so-called scalar multiplication. Right, so you have the scalar multiplication simply means that alpha, let's say 1, 2, 3, 4, the matrix is just alpha, 2 alpha, 3 alpha, and 4 alpha. You multiply each term in the matrix by the number. That's what we are going to call the scalar multiplications, right? So that's what we're going to call the scalar multiplications of two matrices. But what is a matrix of multiplication? Well, if you have a matrix A, this is very more sophisticated. Multiply by another matrix B, how are we going to do it? Well, are we going to assign same matrix, like same size? For example, A is 1, 2. Can you multiply by 1, 2? Well, that's not possible. Okay, so what's the general way to multiply two matrices? So that's kind of nice question. So suppose the matrix A is 1, 2, 3, 4, let's say 6, 5, and 6. The matrix A, what kind of matrix can it multiply? Well, it can multiply a matrix. Okay, so you have three terms, I mean 3 columns in a row. So you must multiply, like, for example, 2, 1, 3. Is that good, Fabric? Now, in terms of the number of columns for the second matrix, it doesn't really matter. Okay, so it can be 1 column, 2 columns, 3 columns, 4 columns. It's only an important thing is that the number of rows, right? So the number of rows means how many terms are in this column. The number of rows for the second matrix should be equal to the number of columns for the first matrix. Why is that the case? Because in the multiplication, what we want to do is that the multiplication is going to multiply the first row with the first column. So what happens here is that it will result in a 1 multiplied by 2 plus 2 multiplied by 1 plus 5 multiplied by 3. So what happened here is that I use the first row in the first matrix multiplied to the first column in the second matrix turn by turn, 1 by 2, 2 by 1, 5 by 3. That's it. And this one, same thing. So it's a 3 by 2 plus 4 by 1 plus 6 by 3. You calculate the numbers, it's equal to something. Is that good, February? So in general, what happened here is that if you have a matrix of the form A11, okay, so A1n, right? So let's say A1m, right? So A1m and A21, okay, so A2m and dot 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 AN1, okay, so ANM. Then you would like to multiply a matrix of the form B1, okay, so B1, 1, okay, B21, okay, so and BM1. Is that good, February? Okay, so and you can result in a B1K, okay, B2K, okay, so and BMK, so that you can see that the number of rows in the second matrix is equal to number of columns in the first matrix. Now the result will be a matrix, right? So of the form like A11, B11 plus dot 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 plus A1M, BM1. So you are using the first row multiplied by the first column. And you continue to do that. Okay, so then you're going to see that in the end, this is A11 B1K plus dot 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 plus A11 A1M, right? So A1M BMK, etc. Is a good fabric, right? So what's the size of this matrix? How many rows do you have? Well, the number of rows is just n, and how many columns do you have? The number of columns is equal to k. So that means you're using m by m matrix multiplied by m by k matrix. You result in a matrix of size m by k, no matter how you choose m. So this is kind of this non-trivial operation, which we're going to call it the matrix multiplication. Okay, so it's kind of not non-trivial operation. It's called a matrix multiplication. Right, so it's not a simple algebra. It's due to theorist, probably a Scottish mathematician. Okay, so the J.J. theorist. Okay, so how you multiply two matrices. Okay, so how you multiply two matrices. Now, once we have all these operations about addition, multiplication, subtraction, right, multiplication, you are going to talk about the properties of matrices, right? So the first property is very simple. You have two matrices, you add them together, A plus B. It's the same thing as B plus A. You switch, and you can simply justify this by yourself. Okay, so A plus B plus C is A plus B plus C. The number alpha multiplied by A plus B is alpha A plus alpha B. Alpha plus beta multiplied by A is alpha A plus beta A. AB multiplied by C is A multiplied by BC, associativity. This is like distributivity. A multiplied by B plus C is AB plus AC. But however, the very important thing for matrix multiplication is that A multiplied by B may not be equal to B multiplied by A. So that's what we call the non-commutativity. Right, so the matrix multiplication is not commutative, right? So you multiply two matrices. It may not be equal to the multiplication of the switch. You switch these two matrices, then multiply may not be equal to each other. So that's we call non-commutative. So you can easily check this. For example, A is 1, 2, 3, 4, right? So let's say B is 2, 4, 3, 1. So that A multiplied by B, by our definition of multiplication, is like 1, 2, 3, 4, 2, 4, 3, 1. You multiply them together, 1 by 2, 2 by 3, so that's an 8, right? 1 by 4, 2 by 1, that's a 6, 3 by 2 is 6, 4 by 3 is 12, so that's 18, 3 by 4 is 12, 4 by 1 is 4, 12 plus 4 is 16, right? So, but what is B multiplied by A? B multiplied by A is 2, 4, 3, 1 multiplied by 1, 2, 3, 4. That's going to result in what? 2 by 1, 4 by 3. This is actually 2, so 12, that's a 14. This is 2 by 2, 4, 4 by 4, 16 is 20. 3 by 1, 1 by 3 is 6, 3 by 2 is 6, and this is 10. So this is exactly not equal to each other. Is a good fabric, right? This matrix and this matrix are not the same. So that's kind of very important that you have two matrices, you multiply them, they're not necessarily the same thing as you switch these two matrices and then do a multiplication again. So the matrix multiplication is not commutative, right? So it's not commutative. This is very important, especially important for so-called uncertainty principle. Right? So if you have been studying physics, uncertainty principle is very important in quantum physics, in quantum mechanics, right? So, and this is very important. So in quantum mechanics, all the mechanical quantities are not measured by numbers, they're measured by matrices because they are operators, right? So if you study any physics, they tell you this. And very important thing on uncertainty principle is that, for example, you take the momentum, right? So you take the position minus the momentum operator, position operator, momentum operator. Then you're going to have the Planck constant, which is that's not equal to 0. Is a good fabric, right? So this is why this matrix multiplication, which is non-commutative, becomes very important in physics, right? So it's one of the very important principles in physics. So now we've been talking about the determinants, right? So we've been talking about the determinants, right? So I've been actually telling you the method of calculating the determinants even before the pandemic, right? So for example, if you have a matrix, let's say A, B, C, D, how do you calculate the determinant of that matrix? Sometimes you write the determinant, or you can just write A, B, C, D with two long arrows. It simply means AD minus BC. Is that good for everybody? But if it's a 3 by 3 matrix, then you have to use this A11, let's say A12, A13, A21, A22, and A23, right? So let's say A31, A32, and A33. You want to calculate determinant, then there are two methods to do it. One method is to calculate, okay, so A11, A22, A33, right? So A12, A13, A23, right? So A21, A31, and A32. You do this, then it's same thing as you calculate this 3, and you calculate this 3, and you calculate this 3. So there with a positive signs. Is that good, traveling, right? So there with positive signs, right? So, and what about negative signs? Well, the negative signs are the off-diagonal terms. This 3, this 3, and this is 3. They are off-diagonal terms, right? So that's kind of what happens to this. So what happened here is that it should be equal to A11, A22, A33, plus A12, A23, and A31, and plus A21, I mean A21, A32, and A13. So this is 3, right? So, and then with the minus signs, the minus sign should be given by the off-diagonal terms. So they are A13, A22, and A31. And then the off-diagonal terms are this is off-diagonal, right? So, and then you're going to have this off-diagonal, you're going to have this off-diagonal. So that's A12, A21, A32, and subtracting is A11, right? So A23 and A32. So that's kind of the diagonal and off-diagonal terms, right? So calculate the term. But there's another method to do it, right? So there's another method to do it, which we call it the Laplace expansion, right? So there's another way to do it, which we call Laplace expansion, which is a much better method, right? So a much more organized method. So what's a Laplace expansion? Laplace expansion simply says that you take A11, right? So A12 and A13, A21, A22, right? So A23, and you take A31, A32, and A33. You want to take a determinant of this matrix. You want to take you just select, for example, I select the second row. You can select arbitrary columns and rows. Then you're going to have A21 multiplied by the cofactor, right? So plus A22 multiplied by the cofactor plus A33, A23, right? So A21, A22, A23, cofactor. The cofactor is simply formed by, you take this element A21 here, you just delete the column and the row containing this. So the cofactor is like A12, A13, A32, and A33, right? And if you have A22, then the cofactor becomes A11, A13, and A31, A33. You just delete the column and row containing that factor. A21, A23, you have to delete this one. So you have this 4 remaining. So there are A11, A12, A31, and A32. Is a good family. But you have like factors of -1 multiplied by the number of row minus number of columns. So this is 2 plus 1, right? So this is -1, 2 plus 2, and -1 multiplied by the number of row plus the number of columns. This is 2 plus 3. So that's kind of the way how you expand a determinant using the Laplace expansion, right? So that's the way how you expand a determinant using the Laplace expansions. Okay, so using the Laplace expansions. So this is about how the determinant is going to enter through these algebras. Okay, so now very important thing. Okay, so very important thing for matrix operation. That so far we've been talking about addition. We've been talking about multiplication, various types of multiplication. We've been talking about how you take determinants, but we have not been talking about how you do ratios. For example, what does it mean if you have one matrix divided by the other matrix, right? So this has been, this is something we missed. We didn't talk about ratios. Now, how do you take ratios? So Are you only supposed to do A divided by B? Well, it's not really the case, but we're going to say A multiplied by B inverse. Is that good, but right? So remember that you can think of this B inverse as a reciprocal operation. If you have a number multiplied by the reciprocal of another number, it simply means that you are doing a ratio between these two numbers. So that's kind of a natural way to talk about the ratios, right? So, but how are we going to exactly do this? How are we going to exactly do this? Well, we're going to exactly do this by introducing what is an inverse. What is an inverse, right? If you give me a matrix A, what does it mean the inverse of that matrix? Well, to this end, I have to introduce the identity matrix first. Identity matrix means you have ones on the diagonal and zeros everywhere else. For example, if I write I2, it means 1, 1, 0, 0. If I write I3, it means 1, 1, 1, and 0, 0, 0, 0, 0, 0. Is that good? Okay, so these are about the diagonal matrices. Okay, so these are about the diagonal matrices, right? So now what does it mean to take an inverse of a matrix? Well, you take an inverse of a matrix, it means that A multiplied by A inverse is identity, and A inverse multiplied by A is the identity. Is a good right? So that's the A inverse is such a matrix that if no matter you left multiply or right multiply the original matrix, you must end up with the identity matrix. Okay, so now how are you going to do that? Very important. Okay, so this I'm going to put 3 stars here. Very important thing for your upcoming final exam is that if I give you a matrix A which has the form A, B, C, D, it's 2 by 2 matrix. Can you calculate A inverse? So there is such a formula that I would like everybody to remember. It's AD minus BC multiplied by the matrix, where you switch the diagonal and you take an off minus sign on the off diagonal. So what happened here is that what is this AD minus BC? So AD minus BC is nothing but the determinant of A. Is that good? Okay, so the inverse of a 2 by 2 matrix is simply taking 1 over the determinant, and what you do is that you switch the diagonal. So remember, it's a switch the diagonal. Okay, so remember, switch the diagonal and take negative sign. Okay, so take negative sign on off diagonal. Right, so you switch diagonal, take a negative on the off diagonal. So that will be the inverse. How do you justify that? Well, you have A multiplied by A inverse. It's like AD minus BC. Then you have ABCD multiplied by D minus B minus C and A. So you have these two. So that means you're going to have AD minus BC. And these two matrices are AD minus BC. So AD minus BC. And A multiplied by minus B, B multiplied by A is 0. C, D, D minus C is 0. So that's AD minus BC. So that will result in the matrix 1, 1, 0, 0. Is that good? But same thing to check the A inverse multiplied by A. After the same operations, you're also going to have 1, 0, 0, and 1 identity matrix. So that's kind of very important. I would like to re-emphasize that if you have a 2 by 2 matrix, then everybody must remember this formula. This is a very important formula. Everybody must remember it for your final exam. It will be very useful for your final exam. Suppose you go to the final exam, they ask you to calculate the inverse. It won't take you, I mean, it is reasonable that you just write down this formula. You don't have to explain it. Okay, so no reason, not a point at all to explain it. But if you don't know this formula, it might take you a lot of time on the final exam. Is that good, February? Okay, the very important thing is to memorize this formula, especially for your final exam. Okay, so let everybody know this. Okay, so this is especially important for the final exam. Okay, so this is what we talk about. How do you take the inverse of matrices? Okay, so and how do you take the inverse of matrices? Okay, so in particular for 2 by 2 matrices. Okay, so now let's come back to our differential equation stuff, right? So you want to solve like the equation x of t, right? So it was something like this: dx over dt is a matrix pt multiplied by x plus qt, right? So something like this. And you would like to kind of compare this with the first order equation. X is pt of x plus qt. How do you solve for that x? How do you solve for x? Well, you have to x equal to something. You have to introduce the so-called integrating factor. Right, so you have to introduce the so-called integrating factor, which is mu of t is exponential raised to the p of t dt. You integrate it, integrating factor, right? So, and therefore, you would like to consider the similar integrating factor like p of t dt here, but this is not reasonable at all. First of all, you give me a matrix. What does it mean, the integral of that matrix? And even if you have the integral of that matrix, what does it mean, an exponential raised to an integral of that matrix? Is that good, Fabulous? So this is kind of unclear, right? So this is kind of unclear. So you do have to have the so-called matrix functions. You do have to take into account to consider the matrix function. What does it mean, matrix function? Matrix function is like this p of t. For example, if it is 2 by 2, it will be like p11 of t, p12 of t, p21 of t, and p22 of t. These are like terms. Each term of this matrix is a function. Is a good family. How do you operate on matrix function? For example, what does it mean, the integral of p of t dt? Right? So what does it mean, the integral of a matrix function? Right? So that's kind of the same for matrix functions. And in terms of matrix functions, the operations are very similar to functions. For example, if you want to take a derivative of a matrix function, okay, so let me consider the matrix function. A of t is equal to a11 of t, a12 of t, right? So let's say a21 of t, a22 of t. This is a matrix function. I would like to consider the derivative of that matrix function, dat over dt. Then you're going to just say a11 prime of t, a12 prime of t, right? So a21 prime of t and a22 prime of t. You just take derivative term-wise. And as we said before, what's the integral of at dt? Well, the integral is just the integral of a11 of t dt, the integral of a12 of t dt, the integral of a21 of t dt, and the integral of a22 of t dt. Just integrate term-wise. That will result in the integration of this matrix function, right? So that's kind of how you operate on matrix functions, right? So here's a nice example I'd like to show you. For example, if a of t is sine t, cosine t minus cosine t sine t. Okay, so let me show you such an example. Okay, so example. Okay, so example is the following. So suppose a of t is equal to, as we said here, it's equal to sine cosine minus cosine sine. Okay, so it's a sine t, cosine t minus cosine t and sine t. Suppose matrix like this. Then can you calculate dA inverse divided by dt? So you want to calculate A inverse. How do you calculate A inverse? Remember, it is 1 over the determinant of A. You switch the diagonal. Switch the diagonal. It's a sine t. It's a sine t. You just switch. This is still sine t. You take a negative sign on off diagonal, minus cosine and cosine. Determinant of A sine square, cosine square is 1. So that's a sine t minus cosine t and cosine t and sine t. So that's A inverse of t. It's a good try. But if you want to take a derivative of A inverse, dA inverse over dt is cosine t minus cosine t is equal to sine t. Cosine t is minus sine t is cosine t. So that's kind of how you take the inverse of that matrix. Cosine sine minus sine cosine, minus sine cosine. Is that good try? Okay, so that's how you take the inverse of this matrix. Okay, so now the matrix differentials, right? So the matrix functions can serve as the solutions of differential equations. Okay, so the matrix functions can serve as the solutions of differential equations. Okay, so for example, here's a question: can you verify that the matrix function x of t is e power 3t, e power 2t minus 3, 4 is a solution of this differential equation x prime 114 minus 2 of x? How are you going to check that? Well, you can kind of, this is kind of like a matrix differential equation. Okay, so I mean, you can talk about this type of matrix diffuse. So how to do that? Well, you have x of t, right? So x of t is equal to e power minus 3t, right? So, and e power of 2t, right? So e power of 2t, and then you have 2 times minus 4 e power minus 3t, minus 4 e power minus 3t, and then you have e power of 2t, right? E power of 2t. You would like to consider x prime of t. And what is x prime of t? It's minus 3 e power minus 3t, 2 times e power of 2t, minus 4 minus 3, so that's like a 12. 12 e power minus 3t, 2 times e power 2t. How are you going to rewrite this matrix? Well, we're going to write everything. Okay, so we're going to write everything as 1, 1, 4, minus 2. Okay, so that's going to be 1, 1, 4, and minus 2. Just multiply by x itself. E power 3t, e power 2t minus 4 times e power 3t, e power 2t. You can see that it works. For example, this is e power 3t minus 4 e power 3. So that's minus 3 e power 3t. And you have e power 2t power 2 times. So this is actually 1, 1, 4 minus 2 multiplied by x. So this is it's kind of already very close to our target. Our target is to solve like a differential equation of this type. Suppose you don't have the q, then you can really have the dx over dt is a matrix multiplied by x, something like this. X prime is a matrix multiplied by x. Okay, so this is very kind of fundamental to our future analysis. Okay, so this is kind of fundamental to our future analysis is about the matrix. Matrix operations. Okay, so matrix functions, right? So the matrix functions can bear with either integrals or differentials, right? So that's kind of a very important thing for matrix functions. Okay, matrix functions. Okay, so and here now I would like to spend about 10 more minutes. Okay, so we would like to spend about 10 more minutes to talk about the systems of linear algebraic equations. Okay, so we'd like to talk a little bit more about the systems of linear algebraic equation. And why do we like to talk about it? Well, it is kind of related to the Wronskians and all this other stuff that we have been talking about before. Okay, so it's kind of related to the Wronskians and all this other important stuff that we have been talking about before. Okay, so and so that's kind of so far we've been considering differential equations, but we have never been talking about algebraic equations. Suppose the class is very general. It's a very general class talking about any equations in mathematics. Then you should talk about the system of linear equations. Linear, okay, so let's say algebraic equations. It's not a differential equation, but it's an algebraic equation. The good family. How do you consider algebraic equation? Well, algebraic equation can be solved of a11 x1 plus a12 of x2 plus dot 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 plus a1n of xn is equal to b1, and a21 of x1 plus a22 of x2 plus dot 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 plus a2n of xn is equal to b2, etc. So an1 of x1 plus an2 of x2 plus dot 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 plus ann of xn is equal to pn. So that's kind of what we call a system of linear algebraic equations. Is that good, family? Okay, so that's kind of what we call a system of linear algebraic equation. But in a compact form, you're not going to write everything like that, but you're just going to say ax equal to b. Is that good, family? What is A? Well, A is the coefficient matrix A11, A12, dot, 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 A1n, right? So A21, okay, so A22, dot, 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 A2n, and etc. So AN1, AN2, right? So dot, 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 ANN, that's an A. And for the x, you can simply consider a very simple state that x is equal to x1 up to xn, and the b is equal to b1 up to bn. So that's kind of very simple. For ax equal to b, that's a system. This is a linear equation. It's a good family. Okay, so now the question is how do you solve such a system of linear algebraic equations? Well, we have very similar notions as differential equations. For example, you have this is like a differential equation, but now it's algebraic. So if the right-hand side is 0, we say it's homogeneous. So that means the homogeneous equation has the form AX is equal to 0. The non-homogeneous equation, okay, so the non-homogeneous equation is simply like AX equal to B. Is that good, family? Okay, so let's say B is not equal to 0. If homogeneous, we say AX is equal to 0. Okay, so that's the definition of homogeneous and non-homogeneous equation. Now, how do you solve? How do you solve this equation? Well, you solve this equation very simply. So you take AX equal to B. There's a very simple way to solve it, is to say X is equal to A inverse of B. By A inverse, we've been talking about it before. It means A multiplied by A inverse is A inverse multiplied by A is the identity. So that's the inverse matrix. Once you have the inverse matrix, you can simply multiply A inverse on both sides of this equation, and A inverse multiplied by A is the identity. Identity multiplied. So the identity matrix is such a matrix. It multiplied by any matrix, no matter left or right, it is equal to that matrix. Is a good family. In particular, identity matrix multiplied by a vector is equal to that vector. Is a good family. So that means this one is the identity matrix, which can simply cancel. And thus X is A inverse of B. That's the solution. So this is a kind of very simple way to solve a system of algebraic equation. You simply multiply the inverse on both sides of this equation. Okay, so on both sides of this equation. But when do you have a solution? Well, it has a solution. You have two facts that we would like to talk about, right? So, for example, if you want, so fact one, okay, so fact one says that if you want to have a solution, AX equal to B has unique solution. Unique solution must take the form X is equal to A inverse of B. When do you have the inverse of a matrix? Well, you have the inverse of a matrix simply when determinant is not equal to 0. Remember this. If the determinant is non-zero, the matrix has inverses. Is that good, trouble? Okay, so now the fact 2 says that, so let's consider AX equal to 0. Can you tell me, I'm only going to ask you only one question for today's class. Suppose AX equal to 0, can you give me automatically a solution? Suppose AX equal to 0, can you give me automatically a solution? Anybody can answer this question before we close today's lecture. Suppose AX equal to 0, anybody has a solution? X is equal to what? Any idea? Zero vector, right? So I like your answer. Okay, so you made my day, right? So this is the only question I could say. If you have AX equal to 0, the solution obviously can be X equal to 0. Now if the determinant, okay, so remember this first fact. If the determinant A is not equal to 0, you must have a unique solution. That means there's only one solution. Now if AX equal to 0 has a solution X equal to 0, and the determinant of A is non-zero, it means the only solution is X equal to 0. Is a good favorite, right? So let me say, suppose it has another solution, another non-zero solution. Then what do you mean? It means that the determinant A must be equal to 0. Because if it's not equal to 0, the only solution you can find is 0 solution. If there is a non-zero solution, it means the determinant is not equal to 0 at all. Is a good favorite is equal to 0. I mean, it's not equal to not 0 at all. So it must be equal exactly to 0. Is a good favorite. So these are very important two facts. If the determinant is non-zero, you have a unique solution. If the determinant is 0, it means the homogeneous equation may have different solution. In particular, it might have non-zero solutions. Okay, so that here the second fact says that if Ax equal to 0 has a non-zero solution, determinant must be equal to 0. Is that good, family? Okay, so this is kind of very important thing. Okay, so this is kind of very important thing for the round skins and the linearly independency, which I'm going to talk about